Okay, now let's say the problem has k independent dimensional parameters, u1 up to uk, and I can say u1 is a function of u2, u3 up to uk. As you can see, u is any arbitrary dimensional parameter involved in the problem, and there are k of those parameters. So if I combine them together and I create dimensionless parameters, each parameter is called one pi term. Pi term. And then I can write in this way. For example, pi 1 is a function of another pi terms, pi 2, pi 3, up to the end. The question is this, first of all, how many pi terms I can create, I can generate for a specific problem? On the other word, let's put the problem in this way. If k is the total number of dimensional parameters, then R is number of references. So remember, the reference can be geometrical or flow parameter or fluid parameter. Therefore, in our study, R should be less than 3, at most 3, if we have all geometrical, fluid parameters and flow parameters. Therefore, N, which is number of pi terms, is gonna be k minus R. This outcome is addressed as pi Buckingham theorem, or sometimes shortly Buckingham theorem. So pi Buckingham theorem answers this question. If such a relationship is given, how many dimensionless parameters or how many pi terms I need to generate, or I can generate out of these given dimensional parameters. That's this value. You might say, ask that, okay, this pi Buckingham theorem doesn't show us how I can generate those pi terms. Yes, you are right. This pi Buckingham theorem fails in the answer of this question, that how I can generate those pi terms. It's not the responsibility of this theorem. The only responsibility of this theorem is the number of involved pi terms in the problem. Therefore, the last one here should be pi, and the subscript or index is k negative R. This is what pi Buckingham theorem, this theorem can tell us. Let's explain this in a short example. Okay. It's an applied example. Assume there is a bridge. So it's a structural bridge, and the flow of air is coming. So it is exposed to the flow of the air, V. And the dimensions of the bridge is an elliptical shaped bridge. So the dimensions is D, a small diameter, and H, which is long diameter. Due to the flow around that, you can see some vortices form. These vortices move with the flow stream and they disappear at the end. This is called vortex shedding. Vortex shedding means that the vortices become smaller and smaller and then they disappear or vanish suddenly. The frequency of this vortex shedding, which is denoted by omega, is purposed. So in general, for example, we know that, so the purpose or what we are asked is vortex shedding frequency in terms of involved parameters. Okay, for example, omega can be a function of geometrical parameters, D and H, for sure, it's obvious. These are geometrical parameters. Also, it depends on the fluid property here, rho and mu. Also, flow property V. After some experiments, we can find this. In the first glance, it's not evident, but this is given to you. So, for example, you can see, okay, it is not very uncommon that we assume that this vortex shedding frequency can be a function of D and H, the dimensional or the size of the structure, rho and mu, the property of the fluid air, and V, the property of the flow. So number of K is 1, 2, 3, 4, 5, 6. The reference values are, these two are reference 1, geometry, let's say geom. These two are reference 2, which is called fluid property. And this is flow property. So all three are present here. Therefore, according to Buckingham theorem or Pi-Buckingham theorem, it's going to be N is going to be K negative R, which is 3. So I expect to see 3 dimensionless parameters in this problem. For your information, those 3 would be this. The first one, the easy one, is D over H. See, it's just length ratio, simple length ratio. 2 involved lengths are dimensionalized with the aid of each other. So it's pi 1. The second one is rho mu v. So you can see it's Reynolds number, rho v d divided by mu. It's Reynolds number, but we call it pi 2 in this context because I just want to emphasize that it's one of the pi terms that it has already been discussed. And the last one is omega d over v, which is pi 3. The third one is also familiar. It's a Strouhal number. Again, it's not the purpose of this class to tell you how you can generate or how you can extract these pi terms from the given problem. But 2 things I want to mention. First of all, the number of pi terms are 3. Second of all, when you generate some pi terms, some familiar ones appear. And those familiar ones are based on the physics of the problem. It is not very uncommon that I anticipate to see a Strouhal number, because a Strouhal number says something about the frequency, and the frequency appears in such a problem. Reynolds number in general, it's a very generic and typical dimensionless number, and this geometrical one. Okay. After this example, in the next segment, I'm going to tell you another aspects and advantages of dimensionalizing or non-dimensionalizing the parameters.